I just make it full screen, I think. And I don't need this. I don't need this. So, okay? Okay, good. I'm going to quickly review what we did yesterday, and then there are some other things I would like to talk about that will support what I mentioned yesterday. So again, for the design process, you have a concept, you have initial design, and then you check its performance. Of course, you have production. So you have production. And then you will check its performance. Then you will decide if you want to redesign. So it's like a optimization process, the convergence check. Convergence check. Or quality check, whatever you want to say. And if it's not good enough yet, then you can have some kind of redesign process. Right? This is what we had earlier. And if you are satisfied, so this is like a no and yes. Final result or final product, something like this. And map this whole thing to optimization. This is like your initial guess, right? And basically, this is the convergence check. And over here in optimization, if you want to do optimization, when you move forward, it suggests you a new design. So actually, this already produced a new design based on optimization. Okay, so if you map this design process to optimization, you can think about this whole thing in this way. Okay. Anyway, we made several examples, mathematical examples yesterday. I'm going to make another example again to support what I want to say today. So let's take a look at this particular example. Just very easily minimizing, for example, x1 minus 5 squared plus x2 minus 6 squared. From yesterday, we already know the solution is actually 5 and 6, right? You know. But in reality, it's like we actually do not know the equation. So we cannot just get the solution by observation. It's not easy. If human eye can understand a function that describe performance and variables, the relationship between performance and variables, then human eyes are super powerful. If we are this smart, we can know what is the best solution in everything in our life, but actually we cannot, right? So, like I said, this is like a black box. It's something you actually don't know in reality. In real life, you don't know, usually you don't know the real function. So Usually it's a black box. You don't know what it looks like exactly. Okay, so yesterday, so the methods are one, you can use so-called a gradient based optimization methods. Okay, so what happened was, if I draw a picture, this is the design space. For example, this is the design space. This is x1 and x2. You know the real solution is somewhere here. This is 5. This is 6. You know this is the optimal solution. Okay? But you know this because I tell you, or you observe it. In reality, you don't know. If I draw the contour of the object function, it looks like this. Okay? This is the contour. So when we have an initial guess, our initial guess could be somewhere here. This could be our initial guess. Okay. So let's try to think about what we did yesterday. We studied so-called the gradient, right? What is gradient? Let's truly try to evaluate the gradient. Okay. The gradient is actually 2 times x1 minus 5. Oops. It's happening again. I'm sorry. That means I cannot use OBS. I'm sorry this is happening. No. Oh, like a share screen?
Yeah, can you add
Okay, so I'll share the other one.
Yeah, stop sharing.
Okay, let's try this. Okay. Okay, let's try this. I'm not sure the issue is about the cable or memory, OBS. Try. And then what do I do?
Screen manager.
Oh, okay. Okay. Let's see. It looks like it's. I'm able to connect. Maybe I just directly project by
Zoom on.
the iPad. Yes, by the iPad. Okay, so
Stop sharing.
okay, stop sharing, and I will directly use iPad. But yesterday when I plug in, doesn't. Oh, how are you? Oh, because I'm using this one. Okay. So I just need to do this, and I'm sorry. Let's try this. So I should stop. How do I do right now? Yeah, yesterday we tried. This doesn't work. No, I already unplugged.
Because I remember this one should be by.
Oh, it's like an AirPlay. Okay. It's just like an AirPlay. maybe we are not in the same internet. No, it doesn't work. Let me try something else. How do I get back?
Stop sharing.
Stop sharing. I can try this. Not by the airplane.
Via cable.
Yeah, by cable. Yes, it's better. Yes. Okay. So Zoom can see me. Okay. Maybe this is the best way. Okay. Continue. Yeah. If I truly try to solve for gradient, come. Yeah. The Apple Pen function disappeared. Okay. Hmm, what is that? Oh yes, yes, come back. Okay. Now it works. X2 minus 6, right? So this is the general equation for gradient. And if I say the coordinate of this point is 2 and 3. So the gradient at 2 and 3 is actually 2 times -3, 2 times -3. So it's like -6, -6, right? So correct. Now, if I try to draw a vector in this direction, it's actually going this way. So this is the gradient direction. It's -6, -6. But let's check Newton's method. Newton's method said you should have something like this, minus Hessian inverse times gradient, right? So over here, we can take a look. Here's a negative sign, and here's the direction of gradient. And of course, in Newton's method, it tells us to update its direction by negative Hessian, inverse Hessian. But in this particular case, it doesn't change. Do you want to check? Let me show you. Let me show you how it doesn't change its direction. Hessian for this case would be 2, 2. The inverse of Hessian would be 1/2, 1/2. So if you do Hessian times negative gradient, then you would have this guy multiplying 6, 6. So at the end, you would have 1/2, 1/2. The negative gradient direction is actually 6, 6. So at the end, it's 3 and 3. Okay, so if we move direct to the negative gradient direction, it's actually the reverse, the opposite direction of gradient. So if I make a drawing in the figure, it's going this way. This is the negative gradient direction. So from here, you can tell Newton's method knows where the lowest point is. by checking the gradient, it tells you, okay, move this direction. Okay, and the powerful skill of Newton's method is that it tells you how far you should move along this way. So from here, if I move by 3 and 3, I will end up with what? 5 and 6. Right? Originally 2 and 3, original 2 and 3. If I move by 3 and 3, then you will have 5 and 6. And we know 5 and 6 is the solution. So Newton's method knows, okay, move toward 3, 3 direction. And 3, 3 actually is the desired movement you need to make. However, in this case, you need to know the gradient. Basically, you need to know how to do derivatives. The drawback of this method is for Newton's method or gradient-based methods, what you need actually is you need gradient. Or you can say you need derivatives. So if you need to do gradient or derivatives, usually you need to know the function form. So it's like you need to know what's inside the black box. Otherwise, how do you do derivative? Okay, so yesterday I told you a second strategy. The second strategy is to it's called a finite difference. Finite difference is a way to estimate the derivatives when you don't know the function forms. Okay? So yesterday I mentioned if you want to do finite difference, you should, let me see what I told you. Okay, you should do something like this. This is from yesterday. Okay. So what does that mean? I need to have small increment of values along one direction. Okay, so it's like in the design space, if I use this example again, and then I use small increment, let's say my small increment is, so basically delta is a small increment. Let's say it's actually not small, it's 0.5. 0.5 mathematically is not small. Okay? For finite difference, the small increment should be very small. So if I do that, when if I want to check what would be the gradient, so basically something like this, the partial derivatives, right? And now I don't know the function form. So basically, this is unknown. I don't know it looks like this. I don't know it's actually 2 times x1 minus 5. I don't know it's 2 times x2 minus 6. So what you do later on is use this way, finite difference. So the way you solve it is actually f of the current x. Current x, I will just call it, I will call the initial gas as x0. How about this? X0. Just so that point is x0. And then I need to add a small increment along the first direction, E1, minus Fx, and then over delta. Here I will do this at location at the current point, add a small increment along the second direction. Okay, minus itself over delta. So let's try to solve it. So it's actually like the function value at, what is my current point? It's 2 and 3, right? So I'm going to plug in 2 and 3, but this time I have small increment 0.5 along x minus the function value at 2, 3 over the small increment 0.5. Over here, the second component of the gradient is 2, 3, but this time the increment on the second coordinate. We do this, okay, over 0.5. So this will give you a result, and it's just an estimation by so-called the finite difference. So let's try to solve it. That's one, okay. So if you plug in, the true value would be 2.5 minus 5 squared plus 3 minus 6 squared, right? Minus 2 minus 5 squared minus 3 minus 6 squared over 0.5. Here, similarly, 2 minus 5 squared plus increment on 3.5 minus 6 squared. Here, the same. Right? Actually, over here, these two cross out, right? Then the true math you need to do, 0.5, so 2.25 minus over 0.5. Okay, over here, this is actually also 2.5. Not set the same. Okay. So what is that value? 2.25 minus 9. Okay, so it's negative 3.32. No, 3.6. Oh, sorry. Let me divide it by 6. Yeah, actually multiply by 2. Multiply by 2. It's not divided by 2. My computer is super slow right now. Super slow. Okay. It's actually negative 13.5. Okay. So you can tell it's different. The true answer for the gradient is negative 6 and negative 6. However, the estimation is different. So this is not accurate. However, the direction is the same in this case. So this is only estimation. Okay? So in real life, when you are truly using this trick to solve for optimization, optimal solution, what did you truly do? You have an initial design 2 and 3, right? It's like you decide your initial parameter 2 and 3 and have one production test the performance of the result based on 2 and 3. Now, since you are using finite difference, you actually need to check some values. Which one? This one. You need to know the performance of this guy and also the performance of this guy. So where are they on the design space? It's actually a small increment toward right. So this is 2.5 and 3. And also a small increment on the top. So it's 2 and 3.5. So it's like in order to evaluate the partial derivative along each direction, you have small increment along that direction and test the performance on that particular design. Based on these 3 trials, Newton's method tells you, okay, move to a new direction. So it will tell you at the end, based on Newton's method, it will tell you, okay, maybe you have a new design somewhere here. Okay, then you need to repeat until you converge, right? Then the other iteration, you will check the gradient again by moving the design point along x1 and x2 by this small increment and check the gradient again. And hopefully later on, it suggests you to move to the optimal. And when you are at the optimal, you cannot stop because your current design and the previous design has huge difference. You need to do it again. You check these three points and you realize there's no change based on Newton's method. So at the end, in the design space, you could be testing all those 9 designs. Okay? I hope you understand what does it mean. This is gradient-based approach with estimation of the gradient. And the estimation of the gradient was done by finite difference. Okay? This is not the only way. Today I'm going to show you different methods. So the other way is to have approximation of the function by what I mentioned yesterday, regression, or sometimes people call curve fitting curve. Or there's another name, response surface. Okay. Yesterday I showed you polynomial fit. Remember? Yesterday I said you can have a bunch of data. Let's say this is 1, F2, Fn. You can have m experiments, and you can have a model. Okay, this is the x1 based on the first experiment, x2, also x1 based on the second experiment. This is second experiment, also x1. Experiment n and x1. And for example, if you have a second order model, okay, and yesterday we talked about this already, so I'm not going to go through this again. Just quickly talk about just a quick review. You have this is your model, okay, and you have all the ones, the constant term, and you have your coefficients. So for example, you have this time I use C, coefficient 1, coefficient 2, coefficient 3. You can have n coefficients, right? So m is your number of experiments, right? N is the number of experiments. N is the number of coefficients in the model, okay? So because this is n by 1, this is n by, this size will be n, so n by n, n by n, and so this will be n by 1. Yesterday, we already know I can call this F vector. I can call this X matrix. I can call this, in this case, I call it a C vector. And because X is not a square matrix, I want to know, I need to know the coefficients. So I need to solve for C. Yesterday I told you, you can do transpose and then multiplying yourself inverse times transpose times F. That's your C. Actually, I can just write it in this way. Okay, this is from yesterday. Here, this is, the method is called least square approximation. Okay? So in the earlier example over here, for Newton's method, maybe you test 9 points. You need 9 experiments. Over here, how many you need? What will be the number of M? It could be 10, it could be 20. You need to try more and more until you get good estimation. Okay? So the more experiments you have, you should be able to have better estimation. But how do you choose the experiments? So there are several ways to choose the experiments. We call this design of experiments. Okay, experiments. Okay, so in the design space, x1 and x2. This is where the solution is 5 and 6. You want to test out more and more positions, then you can have good estimation of the polynomial model right here. Okay, so usually you will define a range. Usually you will sample several design points in a range. Okay, what does that mean? That means you could be sampling inside from 0 to 10, and maybe also from 0 to 10. Maybe the real situation allows you to understand it's impossible to have negative parameters, and the maximum value you can have is 10, for example. So where is 0 to 10? If I draw the region, it's gonna be like somewhere like this, okay? So inside this region, I'm testing some points. I'm sampling some points. Basically, I need to figure out the performance of different combinations of points inside the space. Then I will use all those data to approximate the function, okay? So there's one way, the easiest way to sample is so-called the factorial design. Factorial design. So usually it's like a evenly evenly distributed sampling. Okay, so basically you sample the space evenly. So it's like what you can do is you can try to sample x1, for example, 0, 2.5, 5, 7.5, and 10. You also do the same for x2. Okay, let's say this is the location for your sampling. So if I plot out those positions, basically you are sampling this point, and this is your 10, 10 here, here, 5, right? If you truly want to do this, it's like you are sampling those 25 points. You decided to sample those. So when we say design of experiments, actually it's like making a decision of how you sample the design space. And factorial design tells you, okay, that's a try everything. This is like trying everything. So after 25 experiments, you put all those data in here. You can have a really good approximation of the function. If you know the function, you can take derivatives. You can know where is the minimum, where is the best design. Okay? However, sometimes you don't have enough budget for every 25 experiments. So in this case, you need 25 experiments, right? Sometimes 25 is too much. So there is a way that recommend you to reduce the number of experiments. That method is called orthogonal array. Okay. For orthogonal array, I will need to go to the internet. So in this case, let's connect to internet. Then I can show you orthogonal array. I'm almost done for today. This is no better. Okay, thank you. So there's something called orthogonal array, and if you go to Wikipedia, it will tell you what does it mean. Usually we will have, I'm looking for the simplest version. Um, let me use the simplest version. Okay, L, L10. Let me find easiest, this one should be. Let me find one. Hmm. Maybe try this one. I'm looking for one expression, and so you can understand. Because there are different expressions, I don't want you to be confused. Okay, this should be fine for them. Here, this explains pretty well. So this is the usual expression. L with a number bracket B in the power of C. Okay, this is a very good expression. So get back to what we have here. Actually, just L. Let's say I have a number A and B and C. What are those? A is the uh, number of columns, number of levels, and number of rows. Okay. So actually L4. Maximum number of factors. Okay. So based on this one, this is number of columns. This is number of columns. Okay. And B is number of levels. Okay. C is number of rows. Okay. So usually in the orthogonal array, you will have a table. And what is the number of columns? Column. So usually, let's say you have x1, x2, and x3. Let's say you have three variables. So in this case, you will have I don't think this is the usual way. So there are many different ways. I think this one makes more sense. Want to see how everyone described it. Just also type it Taguchi. Okay, Taguchi orthogonal array. Um, here, like this person's note. L8. This is L8, 2 level, 7 variables. L8. So yeah, what I learned is different from uh, that table. So actually, this is actually number of experiments. Okay, and C would be number of variables. That's easier to understand. Okay, so what does that mean? If I have 3 variables and if I want to try 5 different levels, what are their levels? This is like a number of levels. Okay, this is like a 5 levels for each variable. Right, so what would be the possible combination? So it would be 5 squared because here I have 2 variables. So the all possible combination will be 25 experiments. In factorial design, you will test all 2 square experiments. But in orthogonal array, what it recommends is that you don't really need to do the whole thing. Okay, so it's again, if I find an orthogonal array for I'm actually having 3 variables and let's say 5 levels. So 5 to the power of 3. How about this? If we do this, you will see a lot of tables on the internet. 5 level and 3, 5 and 3. Maybe not the 10 yet. Just say 5 and 3. Okay? 5 and 3. I need 3 variables. In 5 levels. Three levels, 5 levels. Here. I hope. There are 3 variables, right? And 5 levels. You see, 700, 850, 1000, 1150, 1300, right? So over here, you see, this is the exact example good for the number I created. They have, this experiment has 3 variables. For each variable, this person designed 5 levels for each one. So for spindle speed, he has 700, 850, 1000, blah, blah, blah. So if I try all possible combination, let me check if the second one has 5 levels. 0.8, 1, 1.2, 1.5, and 2. Yes. The third one, 0, 0.02, 0.05, 0.1, 0.2. Yes. So this is exactly what I mean. It's a 5 level, 3 variable case. So if I define 5 levels and 3 variables, the all possible combination would be 5 cubic, right? So 5 cubic requires how many experiments? 125 experiments. So think about your project in the summer. Can you try 125 times? Impossible, right? If I say, okay, I give you the budget and time for you to try 10 times. Then it's possible. So in this orthogonal array, it recommends a table for you to follow. It suggests you only a few amounts of experiments and a recommended combination of experiments. So for this one, for the first one, it's actually the lowest for first one. 0.8 is also the lowest. 0 is the lowest. So this is experiment number 1. It's asking you to use level 1, level 1, and level 1. Okay? Whatever value you choose, but use level 1. For the second case, second experiments, it's actually level 1, and over here is level 2 and level 2. So for the second experiment, it's level 1 and 2 and 2. So in orthogonal array, you can, just like what I did, Google for a table. It tells you what would be the recommended combination of design parameters for you to do experiments. Actually, this is really useful for your summer project because you have limited time and resources. You cannot do 25 experiments. Maybe you can only do 5 times, but you really want to test out the performance in different combination of variables. So orthogonal array, what orthogonal array did was it made suggested selection of points inside the factorial design. So when you work on the for example, the first experiment it recommend usually is the lowest one at the lower corner. And in this particular case, I think the second one is recommended is this one. Okay, because it recommends one level up in the second variable. So you can see, continue to read the orthogonal array. It's gonna choose some points inside the factorial design, but not every one of them. So in this particular case, you have 25 possible decision, but later on it will tell you to pick up some of them, not every one of them. So if you have a fewer amount of experiments, when you make approximations of your model, the accuracy of the function will be less. However, you save time, you save resources, you save money. So you really need to make a decision. Do you how many experiments you want, and then based on those experiments, how do you want to build a regression model or so-called a response surface? Okay, I think I'm out of time. Professor Kobayashi is here waiting for me. So
I can leave.
I need to catch my flight. So yeah, that's everything I want to cover for this summer lecture. I hope this is interesting for you. If you design, the word design actually is a lot of strategy from the literature, from the experiments. And people created all those methods just for you to make good use of them. And there are so many methods over there. Each method has its own ability. So I hope my short lecturing about design could inspire you sometime in the future. I can tell you when you study for master thesis, there are some methods is so commonly used. One thing is called the Taguchi method. Okay, it's very related to the orthogonal array that I mentioned. Okay, because in your master degree, it's impossible for you to test so many experiments. So they use orthogonal array to reduce the amount of experiments. Okay, and people use response surface a lot. Okay, I will recommend you to figure out those when you truly need those later on. And of course, when they do optimization for master students, they don't usually like Newton's method. They like something called genetic algorithm. Okay? I don't like genetic algorithm. It's a kind of method that relies on random search, but it's a random search with a systematic strategy. We can say that. Okay, so on the opposite of Newton's method or gradient-based approach, we call those random search kind of method evolutionary optimization. So usually there is a really interesting story behind all those algorithms. And the basic concept of those is to do random search. Okay, so I will leave all these for you in your future research, because when you do graduate study, you may need to do those. Okay. Do I have questions from the Zoom or students from in the classroom? Okay, so I'm not going to give any homework assignment for today, so that's it for me. I will be traveling to USA for a conference in the afternoon, and then our Professor Kobayashi, Professor Chen, and also Professor Zhuang, and also two Japanese professors will be guiding you to work on the project. I will be flying back in the final week, and I hope I will see something interesting that you made in the last week. Okay, I'll see you on the last week of the project. Okay, and I think we can take a 10-minute or 5-minute break. Okay, so let's take a 10-minute break, and Professor Kobayashi will follow up. Okay, thank you. Bye bye.